All right. Good afternoon, everyone. So let's get started with today's exercise. So last time we met, I think we talked about the final project. Um, and perhaps it's a good time here to just open up the floor in case anyone has any questions about the final project. All right, I don't hear anything, so I'm going to keep moving. So today we're going to continue and finish our satellite remote sensing exercise. So I share with you a new partial script just a few moments ago on GitHub. I asked you to download that and move into the code folder of your 14 satellite exercise. Assuming you have done that, let's go ahead and launch that RStudio project. And once the project is launched, let's go ahead and launch the script here. Let's see. Other one. All right. I guess does anyone need more time to get to this point? Okay, so if not, then I'm gonna get started. All right, so on the previous, not the past one, but the two classes ago, when we started this satellite, or I guess we started 4 classes ago, but 3 classes ago, well, anyway, it doesn't matter how many classes ago, but we started this with pulling the mean for one of the years first. So we were getting just the mean back from the server. And then the second part of that exercise was to pull all the imagery for the given growing season. So not just the mean of the growing season, but each individual image within the starting and end dates that we provided. As you realized, when we do pull all imagery, there are some dates that there are no images. Some dates have partial images, meaning that we get some pixels, but we don't get all pixels because of the effect of clouds, and those pixels that are classified as clouds, they get removed from the image that we get. So today, what I want to do on this exercise, what we're going to go through is to retrieve the median instead of the mean, green NDVI across the growing season for 3 separate years, the same years for which we have yield data for this field that we've been working in class. We're going to conduct now spatial temporal stability analysis using the median green NDVI instead of yield. And we're going to talk about why we're doing that. And then at the end, we want to compare the spatial temporal stability classes that we created with the yield data versus the ones that we created with the satellite imagery data, in this case, green NDVI data. That's going to be the goals for today. All right, so a quick intro here of why we're doing this. Why am I teaching you this? Well, as you already saw when we did this analysis with the yield data, spatial temporal yield stability analysis is really important. It's a really important piece of information in precision ag because it can set the stage for yield expectation and patterns in space and time for a given field. So we really start understanding what parts of the field are always high yielding, what parts are always lower yielding, what parts are unstable over time. And we can take that information into account when we're determining variable rate management for that, if that's something that the grower is interested. Now, I have a couple of what if scenarios here. What if the grower does not have yield monitoring capacity? So maybe they just bought a variable rate equipment of some sort, maybe a sprayer, maybe a spreader, and they want to apply based on yield zones, but they don't have yield monitoring capacity to know what are their yield zones. How can we create spatial temporal stability classes for a grower that does not have yield monitoring data? Another case here is, what if perhaps the grower does have yield monitoring capacity for some harvesters in their operation, but not for all. So maybe what is very common here in Georgia, especially South Georgia, is to have peanuts as part of the rotation, as one of the most important crops in that rotation. Perhaps the grower may have yield monitoring capacity on their cotton picker, but there is no yield monitoring technology, at least not commercially available, for peanuts. So maybe some years the grower, when the grower grew cotton, they're going to have yield monitoring data, but other years where they grew peanuts, they won't have the data because that technology does not exist. So in those cases, perhaps we can use satellite imagery to create those spatial temporal stability classes instead of yield data. So that's what we're going to try today in this exercise, is to create those zones based on satellite imagery and then compare the zones that we get from satellite to those that we got from the yield data. The setup here is going to be very similar to when we did the mean exercise based on getting the mean grain DVI. So if you can just go ahead and run this chunk here for the packages, these are all the packages that you have already installed on that exercise. So you should have all of them. I left you here, most of this script, as you're going to realize, is going to be already filled for you. And the reason for that is because you have already done a lot of these steps, just in separate scripts, in separate moments. So I do want you to perhaps understand and make sense of that fact, that a lot of the things in this script are just combinations of skills you have already learned in other exercises. So here we're just bringing the field boundary, which is coming from your 0.5 digitizing exercise. Again, if your path does not match mine, you just have to edit your path to match yours. But this file here should be on your 0.5 digitizing exercise in the output folder. So if the code doesn't work for you, you just have to edit the path so that works with the way that you named on your side. I always like to plot things to make sure that it is what we suppose it is. So just a quick interactive map of the boundary. We can recognize it is our boundary. It is in the correct placing. So nothing wrong here. Now we're going to be connecting to that Copernicus European Space Agency server, as we have already done a couple times in the past. So we start by starting this connection here. So it's just basically connecting our local machine to the server. And now to be able to have access to imagery on that server, we have to log in. So you run this next chunk here for login. You open your console so you can see your console. You go to the console and push enter. So it prompts you to log in on their website. Once it prompts you, you just log in and then grant access. You can say yes. Once it says device login successful, you can go back to R again, and it should show here login successful on your console. This is important to happen. If this did not work for you, then you do not have access to the server. You're not going to be able to conduct this exercise. So because that is a key step, I just want to take a quick moment here and check if anyone needs help with this. I did not hear anything, so I'm assuming everyone was able to log in successfully. All right, so again, the goal here is to first pull the median green in DVI for the growing season of 3 separate years. We're going to start off here with the year 2017. Now, on the first time that we did this, a couple of exercises ago, we asked for the mean of the growing season. I think we may have talked about this in this class, as far as when is the mean the same as the median and when they're different. Basically, let's say, imagine that for a given pixel, you extract the green NDVI value of all the growing season for that pixel, which would probably be, if you imagine a plot with time on the x-axis and green NDVI on each date on the y-axis, you would probably start low and then go up and then come down again, right? So that would be the distribution over the growing season. Now, what happens here is depending on the starting date. Well, you know what? Let me draw a map, a plot here, just so it's easier for you to follow with the visual. So give me just a second here for me to pull out my chalkboard. All right, so imagine here that you have green in DVI on your y-axis and time. So green in DVI on y-axis and time on the x-axis. Imagine you pull 1 pixel only of that whole field. Assuming that planting, so let's say planting happened here and harvest happened here. You would probably see something like very low green DVI before planting. And then after planting, it takes some time, it starts taking off. It gets high. It reaches flowering, which is normally when crops are the most have the most biomass, and then starts senescing, and then they're harvested, and boom, it just goes to 0 because now it's been harvested. Normally follows something like this, right? So this is the behavior of a crop pixel over time, over the growing season, with this line here being planting, this line being harvest. Now, what happens is, let's say when we are retrieving imagery for this field, we really don't know when was planting or harvest. We just have some overall idea when those windows happen in Georgia. So let's say that I say when I'm pulling imagery, I say that my planting, or to start pulling imagery here and to end here. What happens is you have all these pixels. So these pixels here, they're very low. And these pixels here, they're also very low. And they're low because there was no crop growing there. It was, I mean, maybe, right? Maybe there was a cover crop before, but let's not get into that. Let's just assume there was no crop growing before this cotton crop. You are incorporating here pixels that have no crop information. They're just soil. If you do incorporate those soil pixels within the window, which is the window that you're asking, which is the red bars here, what happens is you start getting a lot more you start getting more soil pixels in relation to the total number of pixels that where the majority should have been plant pixels, right? Because that's what we're interested in. Because then what we're asking for the field is, give me the mean. So the mean may be around here. Now, if this window that we ask for data contains many pixels where crops were not growing, your mean starts to come lower because those low green DVI values from soil are pulling your mean downwards. They're growing season-long mean downwards, right? So why then are we asking for the median? So now I want to show you something else, which is, I think we already saw this in this class, but I just want to make that point again. So now I'm not looking into green DVI. This is a density plot. The previous plot was not a density plot, even though it kind of looked like that. But now let's look at any variable. This variable could be variable X. This could be yield, it could be gradient TVI, it could be soil properties, it could be whatever. It's just a variable. And then we have the density of that variable on the y-axis. If I have a distribution, so again, a statistical distribution that is approximately normal, like the one I'm showing you, then the mean in blue and the median in pink are pretty close to each other. They're almost matching. Sometimes they're exactly matching. I'm not matching them here because then you wouldn't see one of them. It would be on top of each other. But if the distribution is approximately normal, then mean in blue and median in pink are very close to each other. However, if the distribution of the data is skewed, so let's take a distribution that looks like this yellow distribution I'm showing you here. So this yellow is for another variable, another X variable, where it is skewed, right? We have a higher concentration of points to the left. In cases where we have a skewed distribution, the median would be wherever the highest concentration of data is. So this is the median of this yellow distribution. And the mean is pulled towards those outliers. So the mean of this yellow distribution may be out here because we have this long tail and these points on the tail are pulling the mean towards that side. So what happens is with distributions that are non-normal or they are skewed like this, the median still represents the central tendency, whereas the mean gets pulled away to the tails where that skewness is happening. Why am I telling you all this? Because if we pull the mean, we have to be very careful to really give a range of time that really matches planting and harvest. Because if we give more dates outside of that, we're getting more soil pixels, which are pulling the mean downwards. However, if we use the median, we don't have to worry as much about that. Because even if we give a wide date between planting and harvest, that is not what actually happened on the field, even if we get more soil pixels from those images, but if we ask for the median is still going to be on the peak of that distribution, and it's not going to be pulled out to the tails where we have all the soil pixels. All right, this is kind of like a statistical conversation, so I just want to take a quick moment and ask if anyone has any questions. Yes, Aman.
Like longer period, the data we have, there are more chances that our mean is pulled towards, like, away from the central tendency. So if we have a shorter data, like for example, for a growing season, then we can use mean, right?
Yeah.
If we have
So
using years, that means we should use mean.
Yeah, so Aman was asking here, so if we then ask for a shorter period of time that we want the imagery from, can we use the mean then? Yes, right. So if we know exactly what's planting and harvest, we can give that window and be more sure that we're getting pixels related to plants most of the time, right? But the thing is, sometimes we just don't know those dates, right? And so it seems if you don't know the date, you still want to give a window of time that makes sense, that may be longer than what actual was observed on the field. But then the median helps you to kind of counterbalance that effect of what if your window is too wide and you're getting too many soil pixels. The median is helping you with that to kind of counterbalance that. It's better to take median.
Like earlier we use mean.
So we use mean on the first exercise. Yeah. Here we're going to use the median. Yeah. Well, not necessarily because of that. Just because, like, if we just give a fixed window of time, it's not going to match that field, right? I mean, it's going to approximate, but it's not going to match perfectly. So we're using the median just so we are being more conservative in the side of not allowing the potentially extra soil pixels that could be within the window to pull the mean down. Yeah, so that's why we're getting the median. Right, any other questions? All right, I'm gonna keep moving then. Let me go back to the code. So I'm gonna close this. Yeah, so this is just a lot of comments about what I just showed you, we just talked about. So let's start retrieving data for 2017 first. So remember, we have already pulled the mean for 2017, but not the median. So that's why we're doing 2017 again. So I left you here. This is the same code as before, so that's why it's all here. I'm not changing. So we're getting imagery from May 1st through November 30th, which is a pretty good window for a growing season of cotton here in Georgia. So go ahead and run it. Oh, never mind. I actually forgot to run my process. So start your process here on line 68. Make sure you run that to start your process. Once that chunk goes through, then go to the data chunk. Let's just run that. So you're seeing here that we're getting data from Sentinel-2, which is the same satellite as before. Product L2A, which is the most processed surface reflectance product. That's what we want. We're giving the spatial extent of the field and the temporal extent of this general growing season window of May 1st through November 30th. And then we're asking for 3 bands, which are the green, the infrared, and SCL is a band that has the classification of the pixels based on cloud. So we're going to be using the SCL to remove cloud pixels. This classification is not something we are doing. It's something that ESA and Copernicus already give us that layer. So go ahead and run this. The next chunk, we're just defining our filtering function to remove the cloud pixels. We have already done this in the previous exercise, so nothing here is new to you. So we're creating that function, that filter function first, then we're applying that function to our data and asking for it to be applied on the bands, because the bands are the component, the dimension here that have that information. And then we are finally running this cloud reduced object, which is the one that has the result of applying that cloud masking function to our data. Next, we did our spectral reduce, which here basically is just us calculating gradient DVI. So we already talked about this. This is not new to you. Just go ahead and run it. Now we're going to apply our temporal reducer, which previously we have used the mean. Today we're going to start using the median instead. So if you go there, I left you most of the code. I just left a little bit of the code that was the part that's changing for you to help me here with. So if you come to the 3 dots, delete those 3 dots. Before we had here the function mean, now we're going to have the function median. We need to say x. So x is going to be the object coming through this function here right on top. And then for the median, we're going to have to say na.rm equals true. So we want to remove na values before calculating the median. Otherwise, we just don't get any values if there's an na in that time series. So run our temporal reduce. If you go to the next chunk, we're going to compile this result from the temporal reduce object that we just used above and ask for it to be saved as a GeoTIFF. So run this piece of the code. And basically everything until here, it's all happening in your local RStudio instance. We have not submitted this to the ESA server yet. So now we're going to do that. So on the next chunk, you do here this function compute results, where we send out our results that we just created above and ask for it to be saved on the output folder under the name 2017 median gndvi.gtiff. Go ahead and run it. This is what is actually sending to the Copernicus server. All of the instructions that we coded above is sending there and it's being processed. So on the server, it is pulling our field, it's pulling the dates we specified, calculating gradient DVI, removing the cloud pixels, and then returning one file for us, which is just the median of that year. So for me, it already showed here that this chunk finished running. If it finished running, it means that this image was actually already downloaded for us. So if you go on your Files tab under Output, which is where we asked it to be saved, you should see now your 2017 median green NTVI, which is the name that we gave on that chunk. Does everybody have that layer? Or does someone not have that layer and needs help? All right, I don't hear anything, so I'm gonna keep moving. Now, with this layer downloaded to your computer, we're going to read it into R so we can look into it. So run this next piece of chunk. I already left you all the code there. So we're using read stars. So this is a stars object because gtif is a raster extension or is a raster file extension. So we're using stars because that file is raster. We're bringing in, transforming to the right CRS, renaming that first layer to GNDVI and cropping to the field. All this should be pretty self-explanatory, and we've done this many times. As we print GNDVI median, if you come on the first panel of that print, you should see numbers here. I mean, some NAs, okay, but you should see numbers. If you do not see any numbers, something went wrong. So let's just take a moment to check that. So when I first was developing the script, I did the median function on the chunk above, and I did not specify na.rm equals true. I just said median of x. I got all NAs back when I imported this. So just a heads up. If you see NAs here, maybe there's something that happened on that part of the code above. All right, last chance if anyone has issues and need help with in this point. All right. So we just brought this layer right into R. So as you would imagine, we're going to be plotting it because I want to make sure that it makes sense, right? So the first plot is just a map view. You can go ahead and run it. This is our field. It makes sense, right? We know, so here on this scale, dark, the black color is low green NDVI and the yellow color is high. So it makes sense. We know that this field here has those eroded parts. So it would make sense that they have lower green NDVI. And also, if you remember our EO data, it kind of looks like this as well, right? So it makes sense that it is this way. Well, something else I think is a good reminder, so a lot of times, as you're gonna see on this exercise, this right now is a raster, is a stars object, meaning it's coming from a raster file. But we're going to transform this to vector in a future step on this exercise. At that point, when we transform it to vector, what now are pixels will become mini polygons, right? So right now, each one of these are pixels. Each one will become their own polygon. Now, one of the ways to perhaps differentiate when you're visualizing, differentiate a vector from a raster is that a raster is always rectangular. Even if whatever is inside of it is not rectangular, the raster is always rectangular. It has a bounding box and it has pixels all across that bounding box, which you can see on this field here. So when all of these kind of grayed out cells, they are NAs. When we transform this to vector, all those NA pixels, they will not be transformed to NA polygons. They're just going to be gone. So if you see something like this, where you have NAs on empty spaces, that most likely is a raster format that you're working with. And that's why we have these NAs on the summary here. So all those 2,260 NAs are coming from these cells outside of the field. All right. So now I also left you all the code for us to create a gradient DVI static map for 2017. So you can just go ahead and run the chunk. There's nothing for you to work there. This is how that looks like. It's just a different color scale. Now we're using Virides, but it's the same data, it's the same patterns, it's just a different way of showing, and it's not interactive. It's a static map. Cool. All right. So now the next, so we just pulled the median for 2017. We have that in our computer. We brought that back into R. We checked it. It makes sense. Let's keep going and do the same for 2019. So you're gonna notice here that I changed the object names just so we don't overwrite and don't get confused. So now I'm calling everything _19, just to make sure that we're using 2019 related objects. So here on the data, we're still asking for the same collection. So Sentinel2 product L2A, same spatial extent of the field. Now, what should be the temporal extent? What would you write down here as the date for the starting dates? Let me ask somebody online in Tifton. Luke, what do you think?
Would it just be the same month and day, but for 2019? So that would be May through November,
Right. So
end of November. Yeah.
2019 0501, right? And then 2019 1130. I think that's what we had. Let me double check. So if we go here on the setting data for 2017, yeah, we had 2017 051, 2017 1130. Yeah, so we just want to change the year, right? Awesome. Okay, thanks, Luke. All right, so go ahead and run it. And again, notice that every object now has an _19 next to it, just to make sure that we don't get confused and mix steps from one year in the other. Now, the next part here of applying the cloud reduce to remove cloud pixels, same thing. We just, again, I just added an _19 to the object names, both the objects that we're creating, but also the incoming objects. So the data 19, for example, right here. So you can just go ahead and run this chunk as well. Next step is to calculate gradient DVI. Same thing, same code as before. I'm just adding an _19 to the object name into the incoming data set as well. So we just go ahead and run it. Here on the temporal reduce, same thing as well. And just to call your attention again, we're using the median and we have NARM equals true, which was the same as on the previous chunk that we did for 2017, but just to stress that again. So we're doing a temporal reduce. Then we're going to compile our result again from an object, a new object called result _19, making sure we're doing for the right year around that. And then lastly, we're going to submit this to the server. So we're sending the result 19 object, and notice how I changed the object of the output. Now I'm asking for it to be named 2019 median gradient DVI. Before it was 2017. So go ahead and run that. We're going to give it a moment for it to go through, for our request to go to the server, and the server returning the final result to us in a form of a saved object inside the output folder. Okay, still working on my side. Just going to give it another moment here. All right, just finished running. So now if I were to come here and check my output folder, you should see a 2019 median gradient DVI.gtiff. It should have saved for you in that folder. Now we're going to do the same as before. We're going to bring our 2019 median gradient DVI as a read stars function, transform to the correct CRS, rename that layer as GNDVI, and crop to the field. So go ahead and run it. Again, I want you to check on your side. So if you come on the first panel of that print, you should see statistical summary here. There's still going to be some NAs, that's fine. Those are all those cells outside of the boundary, but you should still see a summary, statistical summary as well. If you're seeing everything as an A, something went wrong. Anyone needs help here? All right, I'm gonna keep moving. Again, we're gonna do an interactive map just to do a quick check. Looks good. You know, probably looks similar to our previous, the one from 2017. At least we can really see those eroded fingers of this field the same way as before. I'm also going to create a static map. So I left you all the code. Just go ahead and run it for the year 2019. So we have that right here to visualize as well. Again, we see that there's some areas of lower green DVI where those eroded parts of the field are. We see some higher green DVI values on the north part of this field, which I think we've seen some of those patterns on the yield data as well. All right, so that's it for 2019. We already did this for 2017 and 2019. Next step is just going to be 2020. Notice again that now I'm naming all those objects with an underscore 20, just so we make sure that we're not using previous objects by mistake and creating a mess in our processing workflow. Again, here I just left for one of you to help me with the date. So now I want to ask Kiathi, what do you think we should put here?
I think it'll be the same dates again with 2020.
Right. So
So that makes it 2020 0501 and 2020 1130.
Perfect. Thanks, Kiathi. All right. So make sure you have those dates. Make sure that you put the right year. So 2020 in this case. And then you can go ahead and run this chunk. We're going to apply the same cloud masking function. I left you all the code because we're just repeating what we already did on the previous years. We're applying the same spectral reducer to calculate gradient DVI. So just go ahead and run it. And then again, we're getting the temporal reduce using the median and asking for NAs to be removed before the median is calculated. So go ahead and run that. We're going to, again, compile the results into this object. Again, notice that we are naming all those objects with an underscore 20 to make sure that we're not overwriting and there's no confusion between which year we're working with. It's very clear. And then lastly, run that compute result. We're going to send our results 20 object to the server and then get back that object from it, and we're saving as a 2020 median gradient DVI into our output folder. So go ahead and run it. Just gonna take a quick moment. it just finished running on my side. So once that happens, if you go to your output folder, you should see that 2020 median green DVI right there, which is on my side. Now that we have that on file, we're going to again import it into our, just like before, I'm just changing the file here. So we're using read stars, changing to the CRS that we want, renaming that layer as GNDVI, and then cropping to the field. Again, I want to ask you to go and check your statistical summary of this. Again, you're going to have some NAs because those pixels outside the boundary, but it should have a statistical summary as well. Again, we're going to be doing the interactive map just to check if it makes sense. It does make sense, right? We see those fingers as lower GNDVI. Very interestingly, though, look at that on the previous year. I don't know if you remember, but on the previous year, we had some high green DVI values around this northern area of the field. Now they're low, which is interesting. And then on the next chunk, we're going to just create that static map for us to look at. So that's what it is. Also, I don't know if you notice, and if you didn't, let me point out. If you were to go back to all the chunks that I created these static maps, you're going to see that all of them have the same scale favorites limits of 0.2 to 0.61. This is what I selected. I decided to use this because that is the range of values across all 3 years. So if you look at the minimum of all 3 years is 0.2, the maximum of all 3 years is 0.61. I just made all those plots with the same range, so they're very comparable when you look at them side by side. And then we're going to combine all of them. We're going to use patchwork and just using that plus sign. It's going to help us to visualize them. You can just go ahead and run it. You can notice that all the green DVI scales are the same range, meaning that a yellow point in 2017 represents the same value as a yellow point in any of the other years. Cool. So let me ask for somebody to help me to interpret what you're seeing here. And there's many ways of interpreting this. You don't have to give me all potential interpretations, but maybe we can start off with at least one interpretation. Let me ask Polly, what do you see here?
Generally, the eroded part has low NDVI, and the year 2019 show a significant patch of low NDVI, green NDVI near the eroded part there on the east center kind of part. Yes, there. And also 2017 and 2019 show kind of the high NDVI in the north part, which is contrary different to the 2020, which show in the north shows less green NDVI.
Right. Perfect. Thanks, Polly. Anyone else wants to add anything that Polly has not mentioned?
I think that across all the years, there are similar spatial patterns you can see, but there are some certain areas where there is like high NDVI, like on the north part specifically, as you mentioned. And as Polly mentioned, there's a recurring that strip with the, low NDVI.
So Amandeep is just saying that there is a similar overall spatial pattern over time, but there is, as Polly was mentioning, higher green DVI values on the northern part in 2017, 2019 compared to 2020. So something else, well, I guess anyone else wants to add something different, that we have not talked about yet? So looking at this data, and at least under the assumption that higher median green DVI corresponds to higher yield, which in cotton, that relationship may not be as straightforward. But at least under that assumption, I would say that maybe 2020 was not as good of a year because I really don't see a lot of yellow, which in this case here means high green DVI. I don't see a lot of yellow in this field compared to other years. So maybe 2020 had a lower yield. I do not remember the yield data to be able to tell you that comparison. We could go back and look, but at least looking at this, that would be one potential interpretation. Also, something that Polly mentioned, but I do want to stress that out a little bit more, is the fact that in 2017, if you look at those eroded fingers of the field, they are not as prevalent as in other years, right? So Polly did mention here in 2019, we have like another whole side of that showing up that is not really showing up in 2017. It is in 2020, but maybe the lower one is not as strong in 2020. So maybe in 2017, maybe it was a better year as far as rainfall. Maybe it was a better rainfall volume or distribution that helped parts of those low GNDVI areas to not be as low. And potentially 2019, maybe it was a drier year, but it was kind of weird because it also has some pretty high GNDVI values, but we also see those eroded parts of the field very distinct there. So I guess it could also be a high precipitation year, because if you think of it, if you have a lot of precipitation and water is eroding because of that, especially if you have high intensity rainfall events, maybe the crops were not there because they were just washed out, especially if that was early in the season. Maybe that could be an interpretation as well. I guess I'm just raising potential interpretations, but these are just hypotheses, right? Of course, we do have the yield data to look back and back up some of these hypotheses, but we're not going to be doing here. It's just for us to kind of think through some of the things we're seeing. All right, any other comments or maybe questions about this data? Median green DVI on a pixel level across 3 years. So one thing I want to also mention, what you're seeing here, the median data for the whole growing season, these are not, they are not an image that you would be able to go back to the time series and see the whole image, a whole date being this. That is not what this is. What the algorithm is doing is going in each one of these pixels, and imagine that you take one pixel and then you plot time versus green DVI for that pixel, and that curve calculates the median. So for each pixel here, the median is coming from the entire distribution of data over the growing season for that pixel. It is not none of these maps are one image in one field. That's not, or 1 year, sorry. That's not what it is. So just to give you that interpretation as well. All right. Any thoughts or comments before we move on? Right, good deal. So we basically have the median data. If you remember, when we did this with the yield, we basically, of course, with yield, we had the cleaned, the wrangled, clean, interpolated yield. That's what we had. That would be the equivalent of what we're seeing now. After that step is when we start calculating the pixel mean across all 3 years, NCV, and then using that to create the classes, right? So if you think back on the yield exercise, this step that we have right here in front of us with the imagery would be the equivalent of the step where we had the wrangled, clean, interpolated yield for each one of the years. That would be the equivalent step of where we are with the imagery right here. So after that step, if you remember, we had to, well, we also did this as far as right now, these layers are raster. I want to transform them to vector. That's going to be easier for us to visualize the data. I left you the code here because there's nothing special about it. The first one is for 2017, and I don't have the year in this name just because it was the first one, but then I added the year on the 19 and 20. So GNDVI median V for vector is starting with GNDVI median, which is for 2017, transforming to SF and just renaming that GNDVI to GNDVI 17 so we know exactly what year that's from. Go ahead and run that. Now notice that this is an SF object, a simple feature object. And instead of having pixels, now we have polygons. Each pixel became a polygon when we transform from raster to vector. We're going to do the same for 2019. If you go on the next chunk, notice that I added the underscore 19 there, so we know what it is. And when we're naming, it's GNDVI underscore 19, so we also know which column belongs to which year when we connect all of them in one object. So go ahead and run that. And the same lastly for 2020. So go ahead and run that as well. After running for 2020, now what we're going to do is before we merge them, I want to calculate the standardized value. Even though green DVI is already ranging from, let's say, 0.2 to 0.6 in our data, I still want to standardize that to the median green DVI of the field. So the code that we're going to do next is basically the same code as what we did for the yield exercise when we did this spatial temporal analysis. I did not leave this to you quite yet because I do want us to think through how or what we're doing the next step, and you're going to help me out on how to do it, which functions to use, because we have already done this. So again, my goal is to calculate the standardized GNDVI, not yield, because this is not yield data, standardized green DVI value, standardized to the median of the field. So this is where the confusion may come, because right now the data we have is the median over time for each pixel. Now I want the median of the whole field, so one value only. So we need that value and then use that value to standardize everything else to it. So you're going to start coding here, start coding with me. We're going to bring, so the object name is the GNDVI underscore median underscore V. That's the one for 2017. I'm just going to print this so you see it has just one column called GNDVI 17. All right, give it a pipe, and now you're gonna code for me. What is the next step in this process? Remember, I want to standardize each one of those pixel values by the median of the fields. What should we do here? Marco, what do you think?
We need to calculate the median for the whole field. So we use the function median. So mutate.
Perfect. Let me just, yeah, you're in the right track. I just want to help you just so we all get standardized. I want to call this column median underscore GNDVI. All right, keep going, Marco.
We can use the function median
Hmm?
of the GNDVI 17.
Perfect. All right, let's go ahead and run that and check what's going on. So if we run it, now we have a column that's the median GNDVI of the whole field on that year of 2017. Notice that this value here is a single value for all the rows on this data set. We just have one median for the whole field, right? And I am going slowly on this concept because we have two medians going on, right? So one, the first median was the one over time, right? So we had a time series of imagery. We got the median of that time series for each pixel. And then we have a map for the whole field that is the median of each pixel over time. Now we're getting the median of the field, right? We're just getting one value for the field. So this value here, you can also think of it as the median over space and time because it is already taking the median on data that has been reduced temporally. But anyways, not to get too confused, but we have two different medians here that we're working with, just so you connect that in your understanding. All right, thanks, Marco, I appreciate it. So next thing is we need to standardize. So let's give it a pipe. We're gonna call a mutate. Just like in the yield exercise, we call this column SY for a standardized yield. Although this is not yield data, I still want to keep the same syntax, just so you remember this is, I basically copied this code from that exercise and pasted here and made some very minor changes, just so you understand how these things are connected and how you can recycle your code as well. All right, so let me ask Benedetta, what would you do here now?
I would do I would put the formula of the standardization.
Also, remember that right now we're trying to calculate the standardized Green DVI for this field, right?
Yes.
So which columns would you use and how would you use them?
The median and GDVI, and the GNDVI is 17.
Yeah, so what we would do is, so we're going to use the GNDVI 17 on top, on the numerator, and divide that by the median GNDVI, right? So that would be the way that we would standardize it and then multiply by 100. So instead of being a ratio from 0 to 1 is a percent from 0 to 100, or larger than that because we're doing by the median, so it's going to go above 100. If we run this and you print it, now we have this column SY, which is ranging from maybe somewhere between 40 and 160%. I do want to round this number here. So the way that we did in class on the yield exercise is even inside of this mutate, you just give a comma, break line. We're going to overwrite on SY. So SY equals to round SY comma 1. So we just round to 1 decimal point. We run that and print it. Now we have our SY with 1 decimal point. Let me go back to the code in case you're still catching up. And then finally here, let's add a pipe. I want to do a dplyr select for us to select just, so now I really don't care anymore about the GNDVI 17 or the median. I just want the standardized value, but I want to call this SY17 because this represents the year 17. So SY17 equals to SY. So we are selecting and renaming on the same step and also keeping the geometry. So if you run that and you print it, you should see now just the SY, which now is being called SY17. So that standardized yield, although it's not yield, is Green DVI and the geometry. So again, if you were to go back to this script that we did for yield, you would see the exact same code. It's the same thing. It's just that in one time we were using yield data, this time we're using Green DVI data from a satellite. All right. Next step, I want to plot it. So I left you all the code again. You don't have to worry about it. if you just run it, this is the same type of map that we were doing for yield. So now everything is centered around 100. So if something is 100, it is a color white. And it means that that value is either really close or the same as the median of the field. If the value is lower than 100, meaning that is lower than the median of the field, it is different shades of purple. And if it is greater than the median, then it is a different shade of green, as we're seeing here. And again, we did the same plot with the same code when we did for yield. So same thing. All right, now the next step is to repeat all that for 2019. I left you the code because we're doing the same steps. The only difference is that we're naming things with a 19 in front of it, so it's not confusing. You just go ahead and run it. Notice that I am renaming that SY as SY19. So when we bring all those three together, we have them, we can tell which SY belongs to which year. And then if you go to the next chunk, I again left you all the code. You can just go ahead and run it. And we can also visualize those. So here in 2019, perhaps is even a little bit more clear that those values on the northern part of the field are above the field median. We see those greens there. And I'm using the same scale, color scale, and the same range. I just ask for the legend to not appear here because when we combine these plots, we just need one of them to have the legends because the legend is the same for all of them with the same breaks and same limits, same midpoints, same colors, everything. All right, and now lastly, 2020, if you go ahead and run the next chunk, I left you all the code already. And again, we're just renaming the SY here to SY20. So it is, it represents the year 2020. We know what year it represents. If you go to the next chunk, I left you all the code as well to create the same plot so we can run it. And just you can tell here that even when you're just comparing within this year, that northern part is lower than the median. That something we observed already. Okay, so now we're gonna plot all of them together so we can visually inspect what they are. You can just go ahead and run this chunk. I left everything for you. And then we get this map right here. So now it's perhaps a little bit more clear of what is lower than the median of each one of the fields. And remember that for each one of these maps, the field median that we used is a different value, right? It's the value that was the median for that year specific. So it's not like we use one fixed median for all 3 years. We allowed each year to have their own field median with which we standardize the remaining data of that year. So when we check this map, you know, I think it's very clear that those eroded side of the fields are all lower than the median. This is something that we have seen with the yield data as well. So maybe we're seeing some signals here that are matching between the satellite imagery and the yield data, which is cool, right? Which is what we were hoping that would be the case. And again, I think here in 2019, we see that on the eastern side, we have more pixels that are lower than the median of that year, especially around those eroded areas. So this is also interesting, right? And also something else I just noticed. Here in 2020, this northeastern sort of part of the field is actually the median of that, the median of those pixels over time in that year is greater than the median of the field, which is not the case in 2019 and perhaps not to the same extent the case in 2017. So maybe whatever happened in 2020 helped that part of the field to be a little bit more healthy overall. All right, so now we're just going to check the summaries of each one of these. So first, the 2017, we see here that, so again, these numbers are a percent of the median of that year. So in 2017, we see that values are ranging from 55% of the median to 131. When we, oops, 131, yeah, need to change here. In 2019, ranging from about 46 to 132 the median of that year. And then 2020, we see that it's ranging from 63 to 130. So kind of interesting because 2020 here is showing a slightly lower dispersion, right? We're seeing a little bit narrower range, especially on the lower side, which is kind of interesting. All right, so we're going to go through this next piece here of the code, and then I'll give you a break. So again, I want to say that this next piece of code is pretty much the same code as we did for yield because they're the same concepts, right? We're just applying those same concepts to different types of data, in this case, gradient DVI. So remember that at this point, so we have the standardized yield within that year for 3 different years. And now we want to calculate the mean of each one of those pixels and also the CV of each one of those pixels. For that, we have to have all these 3 layers together in the same objects. That is what we're doing on this next chunk. So we're calling this SY all, and we're combining the SY17 with 19 and the 20. So if you just run until right here, you would see that this basically just brings together all those cells. One important thing here to say, every time you do a join, maybe using ST join for spatial objects, maybe using a left join for non-spatial objects that are still a data frame, always check if the number of rows are matching what you would expect. Always have to check for that. So here, SY17, if I just print that, 3568 rows. If I print SY19, 3568 rows. If I print SY20, 3568 rows. So all of those incoming layers have the same number of rows, 3568. So once I merge them, I join them, the merged product should also have 3568 rows. Now just with 3 columns, right? And I tell you this because if we do not specify the join here, so let's say if we don't specify this join, I'm just going to comment off so you see. And then it uses the default join, which I think is called ST intersection. If I just run here, the product has 277,000 rows. Clearly wrong, clearly not what we were expecting. So always check, whenever you do a join, always check that the final product has what the number of rows you would expect. Because if it doesn't, then you cannot continue without understanding what happened and understanding if what happened is what you want. Because if it's not, then it's not going to help you. Just a caveat here. So we're just going to uncomment the joins and let the join equals ST equals to go through. Once it joins all of them and the final product has 3568 rows, we're applying functions row-wise. So we need to specify that with this row-wise function. And then we're getting the mean of the pixel, which is the mean of the 3 columns that have the standardized yield, we're getting the standard deviation of those three columns, and then using the standard deviation and the mean across those 3 years to calculate the coefficient of variation. If you remember here, we need the mean and the CV to classify the pixels into one of 4 classes. So if you go ahead and run this chunk, you should still get, again, 3560 rows. And then in the end, you should have your mean pixel and your CV pixel as 2 new columns. All right, well, first, let me ask, anyone has any questions or issues until this point? All right, I don't hear anything. So I'm gonna give you a 5-minute break. And when we come back, we're gonna start doing our classification.
Tell me,
Nothing. Just want to say your name.
is that a skirt?
Hmm?
Are you wearing a
Yeah.
skirt? Nice.
Thank
Looks
you.
nice. I was looking for something. Yeah. Did anybody tell you you're wearing a nice skirt?
Yes.
Who?
Jancy.
No.
Also, look.
Me.
A random girl at the stables.
No. I want to be the first person.
Ah. That was,
Yes.
I think that was the first thing I said rather than good morning. I said, good morning, walked past you, and then you got up and did something, and I was like, dang, that's a crazy looking skirt. I dig it. Not crazy in a bad way, it's crazy in a good way. I love a denim skirt.
Luke indeed was the first one.
Okay. So here's the
I
thing.
take the credit.
Whenever you're wearing something new,
I'm
call
gonna
me
let
every
you know.
morning, like, Holly, come outside. Just outside. To see if you're wearing something.
You look like a binocular. It's like, yeah, that's pretty cool, actually. It looks good. That's I like it. Anyway, go back inside. Don't let anybody see you wearing that.
Yeah, that can work. Because I can't be the last person every time. No. Now we remaining 1 hour. Yeah, we enough for the break. We're taking a break.
Okay.
Yeah.
You ready to go home?
Uh-huh. Okay, yeah.
You're going to total five?
5, yeah, 5.
Five, right?
Yeah,
I'll tell you other guy to go because you want to right now.
okay.
But I still have some.
Yeah,
So
okay.
I'll be around.
Yes, I can give you a ride.
Wow.
Yeah.
All right. Timer is up, so let's resume our exercise here. Okay, so before we get into the classification, let's check the summaries here. So the first one, I want to check the summary of the mean pixel. So it's going from 58 to 117. If we look at the density plots of the mean pixel, just so we understand the statistical distribution, this is how it looks like. So we have a peak around 106, perhaps 104, somewhere in that range. We have a longer tail to one of the sides, and the highest value is 117. Oh, okay. Let me continue on the next chunk, and then I want to ask you all a question. Now, this is for the mean pixel, which is one of the variables that we're going to use to create those rules, to create the classes. Now let's check the CV, the coefficient of variation. So here on the CV, we'll see that is ranging from 0.1, which is a very small CV, to 31, or 31.6 is the maximum on this data frame. And then if we check our density plot of the CV, it's just a different way of looking at that distribution. We see, I mean, the same thing as far as having the mean CV where we had the highest peak here being around maybe 6 or 7, and then the minimum being very close to 0, and then a longer tail with maybe only one observation outside of 30. All right, so I think I'll go a couple more chunks here before I ask for your thoughts. I left you here the code, exactly the same code as we did on the yield exercise, to look at a map of the mean pixel, and the color scale is breaking into 80 and 120 because those were the thresholds that we used to classify based on the mean pixel, if you remember. If you run this is what we see. Now I want to ask somebody, I mean, ask all of you, but maybe somebody to tell me what is going on here. Why do we only have 2 colors on this map? You have 3 colors? All right, Aman has 3 colors. I'm not sure exactly how. Oh, maybe it's because our boundaries are slightly different, and maybe that caused a whole bunch of differences. But let me also ask other people, like, does everyone, or does someone have 3 colors here?
Yes.
I have 3 colors too.
I also have 3 colors.
I have 2.
But the third color is on the boundary.
Very close to the.
Okay, yeah, so that may be just a difference between our boundaries because each one of us digitized independently. But so one thing for us to, well, maybe let's just think about the one that I'm seeing because I think it's going to be easier to make the point with that, but that's going to extrapolate to everyone's after we make the point. If you're looking at my map, so this is the point where we say points less than 80 are low, points between 80 and 120 are medium, points more than 120 are high. If you remember, those were the thresholds that we used in the rules on the yield exercise. Why in my map I only have 2 and not 3 classes?
Because you did the mean.
Can you say that again, Benedetta?
Maybe because you did the mean.
You mean like I got the mean here? Is that what you're saying?
Yes.
So we also got the mean on the yield one, right? I mean, we got median in 2 different steps, but in this step of getting the mean of the 3 years, we did get the mean. And this is also what you all did on your side. So, I mean, it could be related to that, but I guess that is not the main cause. Or not cause, but I guess what I'm trying to get to, maybe let's go and make the next map, which is the CV pixel map as well. So if we do that, if we run the next chunk, look at that. I only have one cell that has a CV more than 30. Everything else is lower than 30. What is happening here is the thresholds that we use on the yield data, those thresholds were established on that paper that you all read that were using those thresholds. However, although those thresholds make sense, intuitively they make sense, but to some extent they are arbitrary, right? I mean, they're not like set in stone that 80 and 120 are the thresholds we should use. What happens is perhaps even with yield data from a different field, perhaps on your final project, you're going to see this, that if the variability of a field is lower, maybe you're not going to have variable enough data to have all that range of values going from, let's say, 60 to 150, and then a CV of 0 to 45. Maybe your data is not as variable that you just have a more constrained range of values. Of course, in this case, we're not working with yield data. It is green DVI data, but this could happen also with yield data. If we go back to our summaries here, where we check the summary. So first, the summary of the mean pixel. Mean pixel is ranging from 58 to 117 on my side. So we're not going to have any pixels that are going to be high yielding if we use the threshold of 120, which is the one that we got from the paper. Similarly, if we look on the summary of the coefficient of variation, the maximum is 31.62. And there is only one cell that has this much CV. Everything else is lower than that. So if we use, again, the threshold of 30% CV to say if something is stable or unstable, we're just not going to get, we're just going to get one unstable pixel. Everything else is going to be stable. I'm telling all that just as a caveat, and we're going to think about this again in a second here. For now, let's just keep moving using those thresholds from the paper, and then we'll talk about it later. All right, so I think we stopped at the plot of the CV with this one. And then the next chunk is just bringing both of those plots together and then just exporting them to your output folder, which is exactly what we did with the yield data as well. You have these same 2 figures for yield when we did the stability exercise. All right. Now, let's actually do the classification because we have not done the classification yet. So let's implement that. So if you remember, and this was a question on your midterm, so I hope that you do remember from that at least, that the way that we did the classification is the first step is to look at the CV of the pixel. If it is more than 30%, then we classify as unstable. And if it stops there. If it is less than 30%, then we further classify it on the yield levels. So if pixel is less than 30% CV and the mean standardized yield is more than 120%, then we classify as high stable. If the CV is less than 30 and the standardized mean yield pixel is between 80 and 120%, then we classify as medium stable. And lastly, if the CV is less than 30% and if the mean standardized yield is less than 80%, then we classify as low stable. And I posed this question here, which I think we just answered, but given the summary that we got from mean pixel and CV pixel, do you think these thresholds would work for these data sets? I hope you have already got to the conclusion that probably not. But anyways, I left you the code here, the same code as we use for yield, to actually apply those classifications using case when. We have each one of the conditions, and then we're just assigning that to this column, ST class. So if you go ahead and run this, now we have a column, ST class, that has all those 4 potential classifications of spatial temporal stability, of unstable, low stable, medium stable, high stable. Now let's plot that. Again, I left you all the code because it is the same code as we did for yield. Just go ahead and run it. This is what we see. So let me ask somebody to help me to interpret what you're seeing here. And I think I have not asked Mohit for help yet. So Mohit, can you help me out here? How would you interpret this map? And you're muted, just to let you know.
Oh, so the map shows different classes like stable and unstable and different like low, medium, and high. The most of the map is stable and is medium stable, and the part of the area which have shown gullies in the map has low and stable yields, and some of the areas on the right side of the field has a high stable yield, and there's only one dot that shows as unstable.
Yeah, so I just want to clarify one thing. So if you look here, we do not have any pixels as high stable. So we're missing a whole category here. Right? So
Okay.
but everything else that you said is completely on spot, right? So we have most of it medium stable. We have some low stable, the blue dots. We have one pixel that is unstable, which is this one right here. And we are completely missing the high stable class.
Dr. Bastos, like in my map, is the high stable class is there.
Oh, really?
Yes.
Okay. So where do you see the high? Is it like?
It's very small, like small dots, like maybe 6, 7 dots on the right side, like next to the gully area on the right side, like there's 5, 7 dots, deep blue dots.
Gotcha. Okay. Well, my apologies then. I guess I was under the assumption that you were explaining the map that we're seeing on the screen. But that makes sense. I mean, it makes sense that we're getting a little bit of different maps just because our boundaries were different a little bit. But at least on my side, we're completely missing the high stable, right? And so I guess bringing back this conversation of the thresholds that we used. So we use those thresholds coming from a paper. So it's easy to cite, it's easy to explain why you use those thresholds. But also keep in mind that maybe those thresholds are not going to work for your data. Again, if your data is more or has less noise, has less variance, less variability over time, you may not have all those values to make all 4 classes. So I guess at that point, you can either decide to keep with the thresholds that we use from the paper and just say, well, this is what it is. I just don't have high stable areas. And my unstable is just 1 pixel. So pretty much non-existent if we're looking in my figure, of course. Or we could go back and maybe play a little bit around with those thresholds, which I think could be useful here for us to at least understand two concepts. One is that although the thresholds make sense, but they're not a hard set rule, right? They're still subjective to some extent. So there is a little bit of room to play with them, as long as you maintain the thresholds you choose intuitive, right? You don't want to say that something that goes from 40 to 60% is high yielding. That does not make sense, right? You still want things to make sense, but those thresholds, you can adjust them to some extent. So that is the first concept. And the second concept is going to be how well our yield data is going to match our green DVI classes. So I want to invite you to go back to the chunk where we have the classification. And I want to ask for your help as far as so this is your field. And again, you're gonna do this exact exercise, you're gonna do with your final projects. So, on your final project, I'm not gonna be there to tell you what to do. So you're gonna have to think through and make a decision on your own. So if you were to change some of these values here to perhaps give your data a little bit more chance of having more classes, what would you change and to what value? The median of the CV?
Yeah.
Okay, so Amandeep here is suggesting that instead of using 30 as our threshold for stable or unstable, that we use the median value of the CV distribution. So where would you find this, Aman? On the summary, right? So if we go back a few chunks, we go to the summary of the CV. This is it. So the median is, let's say, 8. You propose we use that value? Yeah, I think it makes sense. I mean, normally I think a rule of thumb is that something that has more than 10 or 15% CV is like too variable. But I like your idea. I like the way you're thinking as far as using the statistical distribution of that metric and using the median of that distribution to give you a value. I think that's a valid approach. Right, so let's give it 7.5, just to kind of be a little bit closer in rounding up. So 7.5 is going to be, so if you go back to the classification chunk, everywhere that you have 30, just change that to 7.5. So we're going to change 4 times. Okay, so now definitely we're going to have a lot of pixels that will be unstable, right? I mean, we're going to have approximately half of the pixels unstable because we use the median of that distribution, right? Now, as we saw, we also don't have any yield data that the mean standardized number is more than 117. So I think we should maybe play around with this threshold of the threshold of 120. So someone else, let me ask, let's go back to Luke. Luke, if you had to change this value here, this 120 value, what would you propose that you do with that value?
Yeah. Okay. I guess to keep it simple, you could just go to the third quartile for our mean pixel, which is rounds up to 106. You could do 105.
Okay, I like that. So let's change 120 to 105 in 2 places here. All right. I don't think we have to worry too much about changing the 80 threshold because we do have a good number of points below 80. But maybe that could be something you could play around with as well, right? Just to keep in mind. All right, so now that we made all these changes, make sure you run again this chunk, the SY all class. And now we're going to plot again. So the next chunk here that we run. Oops. All right, it's very different looking now. Right, so we really see there's a lot of unstable pixels. We have all 4 classes, at least on my side. So we really can see that. I want to propose that so all the suggestions that Amandeep and Luke gave are completely valid, and I really like that. On the unstable side, at least so we can compare a little bit better with our EO data, I do want to change this to be 20, which is not the median of the CV pixel, but is a little bit lower than the threshold we have initially. So change your CV pixel to be less than 20, and we can keep our 105 as we had before. Run again this chunk. Run again the next one which makes the plot. And then this is what we get. All right. So now we're starting to look a little bit closer to our yield spatial temporal stability classes, right? And I think that one way we can check it out is maybe by bringing the yield-based spatial temporal stability classes back into the script. So I'm using here this piece of code, which is just navigating to my 07 EU monitor project in the output folder where we exported this tab class.png file, which is our classes for our yield-based spatial temporal variability classes. Now, I'm gonna pop this out a little bit so we can see them side by side. So using the new thresholds that we set up here, I think they still have a good amount of commonalities, right? So we're seeing perhaps this area here of unstable pixels close to that gully on this field. Something that I found very interesting, that when I saw this result, I was actually pondering. Of course, we have our EO data as our ground truth, as what we believe is actually happening in the field. But if you think of it, to me, it would make sense that those gullies to be consistently low stable, which we see on the satellite side. We do not see on the yields. I mean, we do not see the gullies on the yield-based temporal spatial classes. So, I was scratching my head and thinking, perhaps when we do the interpolation, so every time we do interpolation, you're averaging out, you're averaging things out, right? So there's a lot of averaging out in many directions. So one is when you interpolate, you're averaging out to some extent. When you do the median over time, of course, we did not yield, well, let me take one step back. On the imagery side only, that we have multiple images in the growing season, we got the median. We're averaging out there. On the yield, we all just have one yield date per year. So we're not doing that with the yield. But then when we calculate the median of the field, we're averaging out. So there's a lot of steps that you're averaging out those tails of those distributions and just getting closer and closer to the mean. So I guess what I'm trying to say is, I wonder if truly those gullies should be low stable as we see on the satellite side, but on the yield side, we don't see because of some of the averaging that happens on the interpolation. I don't know. Also, we see this overall pattern of both of them to have the unstable, the high stable, so the blue ones, the high stable to be more prevalent on the west side of the field, on the left side, although there's a lot more here on the satellite based than on the EO based. And we see that medium stable is still the majority of the pixels. We see some common places where low stable is happening both. But then it becomes a couple, so there's a couple things here. Another way I want to show you is, so let's say that we assume our yield is the truth, that is what our satellite should look like. We could go and play around with our limits of the classification, of course, within reasonable range of values, but we could play around with them and try to get them closer here. So maybe one thing that we could play around is right now we have a lot of high stable that on the yield side, we don't have as many. So if we were to go back again to those thresholds, and instead of using 105, maybe if we use 110, so we make it a little bit more difficult for high stable to happen. So if you do 110 and run the plot after that, this is how it looks like. It starts to look pretty close to the EO one, right? Even though in the EO we're using some different limits, different thresholds, but they start to resemble more each other. So a couple of things here that I wanted to kind of close out with this exercise is, if you were to ask me if we can create spatial temporal stability classes using satellites instead of yield, I would say, yes, we can definitely do that. We just did it. Now, one difference is that we may need to use different limits on our thresholds to get them to look closer to each other. And another thing I want also for you to think with me is that even on our EO data, we just use the thresholds from that paper. But again, there is nothing saying that that paper is, that we cannot change those values to some extent. So potentially we could also go back to our yield exercise and play a little bit around with those thresholds, which are going to change how the map looks like and how the classes are distributed. So both on the yield and on the imagery side, those limits are still changeable to some extent. Perhaps if we had used like Amandeep and Luke proposed, maybe those limits should be based on the statistical distribution of the actual mean and pixel, of the actual mean and CV of the pixel, rather than just fixed values that we just use across all data sets. Maybe that's right. Maybe we should use this statistical distribution of our data to determine what are those thresholds. I don't know. So just some thoughts, more just thoughts in the sense of for you to think through. I really don't have a good answer, I guess, for the questions I'm posing, but just for us to be aware that a lot of these decisions, although as scientists, we want to be very objective, but a lot of times there is some subjectivity to it. And then we just have to ask ourselves, does that make sense? Does that apply to my field? Does that apply to my data as well? So just some thoughts to throw out there to help me and you to think through what we're seeing. All right, any questions or thoughts about this? Okay, so I'm gonna keep moving here. I think this is pretty much the end of this exercise. So just as a quick summary here, on this exercise, we retrieved green DVI season-long median for each individual year of 3 years. We calculated the spatial temporal stability classes based on green DVI, and then compared those green DVI-based stability classes with the EO-based stability classes. Perhaps another thing that we can talk about here is that just happened to me is to mention that, as you know, different vegetation indices have different sensitivities to crop biomass and chlorophyll and health overall. So if we have used, for example, NDVI, I would expect, so NDVI using the red band instead of the green band, I would expect for the variability to be even smaller. Maybe if we used another vegetation index that does not use red or green, maybe the variability would have been wider, and maybe those original thresholds would have made sense. So even the choice of what imagery aspect we want to use can play a role here. So a lot of different pieces moving, right? And again, my goal is just to help you understand that this has a lot of subjectivity when it comes to this use. But nonetheless, we can definitely use satellite imagery to get an idea of the spatial temporal variability of yield in the field, even if you do not have yield data. So a very powerful tool that we have at our disposal, which for research purposes is free, open source, and you just learn how to do that on this exercise. All right. I guess I want to open one more time to see if anyone has any questions or thoughts, either about the class or about the final project. All right, I don't hear anything. I want to let you know that we have one more lecture that has been planned and scheduled, which is going to be from Neva. Neva is a PhD student in crop and soils, working with Dr. Lorena Lacerda on hyperspectral imagery. So Neva is our hyperspectral imagery expert. She has prepared a great exercise for you to learn how to, first, what is hyperspectral sensing? What are the differences between that and multispectral? So for, if you don't remember, satellite imagery that we're using here is multispectral. Also, the drone imagery we used for the variable rate nitrogen exercise was multispectral. So Neva is going to introduce the topic of hyperspectral sensing first, and then you're going to have a lab based on some steps, not all of them, because all of them would maybe take a whole semester, but at least some steps of hyperspectral data processing and analysis. And that's going to happen next Tuesday. Besides that, I don't have anything more today for you all. So if you don't have any questions, then let me open the attendance issue so you can claim your attendance. My gosh, April 17th. Where is time going? All right, make sure you claim your attendance. If you do not have any other questions, you are dismissed, and we'll see you on Tuesday. I'm going to stick around for another few minutes in case anyone has questions. Thanks, everyone.